Okay, good morning everyone. Today I will present you our latest research in image authentication and self-recovery. So, I am Afrik Aminuddin. I am from Indonesia. So, at first I will introduce myself. I got my bachelor degree in informatics at University Amikom Yogyakarta, and then I got my master degree in information technology at University Gajah Mada. And then the latest one, I got PhD in computer science in University Malaysia Pahang. And currently, I am a lecturer in Department of Information System in University Amikom Yogyakarta. And then I will discuss about image authentication and self-recovery. So consider this image. This is an image of airplane, and then actually this image is already tempered. So the actual color of the airplane is not like this. This is the tempered image of the airplane. So in this research, we would like to localize. For say, if this is an entire image, we have to localize which part of the image that already modified, and then here is the result. So our algorithm can localize the modified area of the image. So in this case, the white one, it means that all of the pixel in this white area is already tempered, already modified. And then the next step is how to recover the image, and this is the last one. So after we run the algorithm, so we can recover the image, and then we can clearly recover the image. It is not quite as similar as the original one because there is some information loss, but it's quite similar. I mean, we have uh, a way to measure to count how many pixel that already is that's similar to the original one. So we have the performance evaluation. Later on we will discuss later. Okay, before we go on, I will show you the background of image authentication. So image authentication is divided into two in this research, which is passive image authentication and active image authentication. In passive image authentication, we have no prior data. We have no data on how is the original image and on how is the tampering being made and etc. We have no any data, so we have only the manipulated image or modified video. The task is to use like machine learning or deep learning technique to localize which part of the image that already modified. In some cases, we cannot localize the image, but we can only classify from maybe thousand of image. We can only classify which one of the image that modified and which one the image that is not modified or the original one. So to localize precisely to the image, we use active image authentication. So there are two ways to localize the image. The first one is using digital signature, which the data is embedded into something else. I mean, outside the image itself, the digital signature, maybe you can embed the data using blockchain technology. And then the other technique is using the technique. Watermarking technique. So the recovery data, the authentication data, is embedded into the image itself. So wherever we found the image, as long as the authentication data and recovery data is already in the image, I mean not lost because maybe the whole image is already tempered, so we can, in theory, we can authenticate or we can localize the tempered region of the image, and also we can recover the image. And then in the process of watermarking, we have embedding step and extraction step. in the embedding steps, we use LSB, less significant bit embedding, and then the data to be embedded is authentication data and recovery data. And then in the extraction technique, actually the algorithm is divided into two. The algorithm will support only authentication, and the second one, the algorithm will support authentication and recovery. And then in the authentication and recovery, there is a problem. There's a problem which we call is as tamper coincident problem. To solve this tamper coincident problem, we are using three techniques. Yeah, this is our recent research, which is using block mapping, multiple recovery, or image inpainting. We will discuss it later. So this is the framework of image authentication. This is the input image, and then this is the watermark image. So we run a series of algorithm to produce the watermark image. So once the image is watermarked, then we can send it into a communication channel, which maybe some attack happen, some modification happen there, and then our algorithm is to detect from the tamper image to detect the tamper localization, or we are the task is to localize the tamper image so we can clearly see which part of the image is already tampered or modified. And then after we localize the tamper coincident, we are using image inpainting technique to find or to recover the image into original state, like this one. Okay, we'll discuss this. The first one is the problem is the limited space for recovery data. So here in the watermark generation, we have data to be embedded into the image itself. So like this one. So the cover image, we will divide the image into non-overlapping block of 3 by 3, and then we will find the recovery data here. We will find the authentication data also. So from the recovery data, through the series of techniques or process, finally from 3 by 3 pixel, which is we will find 9 pixel, and then on each pixel we have 8 bit of data, and then we embed the watermark data into the last 2 bit, either in recovery data or authentication data. So we have 18 bit watermark slot. So we can embed the authentication and recovery data into this 18 bit. So we already arranged some kind of authentication recovery data like this one. So this is how we embed the data into the image itself. So as mentioned earlier, we also preserve the texture of each block. So in each block of 3 by 3, we are trying to preserve the texture, but we can see clearly here there are 16 here, 16 possible texture on each image. So to get the maximum performance, maximum image quality, we get 16 here. Why 16? Because we only have like a limited amount of data to store the texture here. So we only have 3 bit of data here. So to store the recovery ID, or if we learn about GPK compression, there we embed the quantization table, yeah, into the TJP itself. So like this one, we also embed the texture into the image itself. So we are so limited here, so we only can store 3 bit here. So only there will be only 16 texture. Okay, and then this is how we define our texture, how we put our texture, the process here. And then the image will undergo underwent communication attack in the communication channel. Various attack here, like image embedding, yeah, like image regular attack, yeah. We'll discuss it later. So here is the example of image tampering attack. Here the original image, and then this is the irregular attack. We place something here, copy paste forgery here, something here, or we have regular attacks. Actually, for regular attack, we use this for the purpose of uh, performance evaluation of the algorithm. So we have like 80% of image tampering, so we can add uh, like from 10, 20, 30, and so on and so on, so we can control the the area of our attack, the attack, yeah. So for irregular attack, we cannot control how wide the area of the attack, like this one. Okay, now and then the task is to detect and localize the tamper area of the image. So here this the watermark image, and then we replace the airplane here, and then we localize the tamper area of the image. And then this one also the original image, and then we attack like the block of image here, and then we can localize the which part of the image that already modified. And then the next one is self-recovery. So in the self-recovery, here is the tamper image, and then this is the first step of recovery, which already see here that there is a tamper coincident problem here. So the information is lost, so we have to recover the part which it has lost information here. So if you see here, this is the part of tamper coincident problem, and the task of the algorithm is to solve this one. So we can see a smooth here, so we can see the original image here. It's I mean it is the recovered image when the quality is like the original one. And this one, the another one from the regular attack, we see that the tamper cohesion problem is so huge here. The task is to recover, and this is our algorithm currently. So yeah, as you can see here, the algorithm is not perfect. In 80% tampering rate, the recovery data or the recovered image is like this one, still not perfect. Okay, we'll go on here. The second problem is tamper coincident problem. Tamper coincident problem is this one. So here, tamper coincident problem, which the information is lost here. We cannot recover the recovery data. So this one, the tamper coincident problem. This one, the tamper coincident problems, and this is also tamper coincident problem. Okay, we will back to basic how to embed the watermark data. At first, we'll generate the block map. Block map means that in embedding the authentication data, we will embed the authentication data into the block itself. So in block 1, we will embed authentication data into the block 1, so into the block itself. But the recovery data of block 1, we will embed into another block, like block 10 maybe, or block 12, so far away from the block 1. So in which case the block 1 is tampered or modified, then we can take the recovery data from block 12 or block 11, and then this recovery data is used to recover the block 1. So this one, at first one, we will generate the block map. So the block map means that where to store the recovery data. So like this one. So in original block location like this one, so the image here 1 2 3, this is the block location of the image. We use 64 block here, and then we can use random block mapping. So it means that block 3 is stored here, recovery data of block 3 is stored here, recovery data of block 39 is stored here, and so on and so on. And then we can count how far the original block and its recovery data, like this one is 2, this one is 6.4, and so on and so on. So we can compute how far is the recovery data located, and then we can plot here. When using a random block mapping, we can clearly see that the most of the data is in high TCP zone. So because this one, it means that the data is located is closely to the original one, like this one. So like 25 or almost 30%, yeah, the data is recovery data is located in the original one. Now this one is the high risk of tamper coincident problem. So the task is how to move this high TCP, high tamper coincident problem into the left one, into low TCP. So we propose using our new block mapping technique. For comparison, this is one for uniform block mapping. Uniform block mapping, it means that all block here in the left top here is located or embedded into the right bottom here, and then this one from the right top will be embedded into here, which is left one, left bottom here, and so on and so on. So we have same Euclidean distance here. So all the Euclidean distance is 5.7 for this one. This is actually quite good one, but it will have a problem. We will tell you later. And this is for our technique using block mapping technique, which is specifically designed for our recent research. Yeah, this one. So it ensures that all the block here, the green one, is embedded into another block, another 3 block here, like this one. So there is no block in this one which is embedded into the same region here, the first region. So all green block are embedded into other region, and then when we calculate the Euclidean distance, we can see that all block is far apart one another. So like this one, this the comparison between random mapping, uniform mapping, and authentication AuSR3 mapping. Yeah, this is actually our new method here. Then this is the random. We can see that using our technique here, the green one, we can move all high risk of TCP into the right one, into here medium or low TCP. So like here, the distance between original and recovery block is quite far. This one. Okay, and then the problem of the second one, we use image inpainting to solve the tamper coincident problem. This is how we solve the problem in image inpainting. Yeah, this is the tamper coincident problem, block with tamper coincident here in the center one. Then we will search the surrounding area which doesn't consider as tamper coincident problem. So like this one, there are A, B, C, D, E, F, G. Then we can predict the value of tamper coincident block based on the surrounding block which doesn't underwent a tamper coincident problem, like this one. Then here our experiment result. So our experiment shows that this technique, our technique, is perform better than any previous method like this one. This is for our whole data set. Yeah, we only use 8 images for the data set here. And then this is the SSIM. The first one is PSNR. So for SSIM, if we close to 1, it means that the recovered image is close to the original image. And this is for tamper localization, for precision accuracy. We can see this one. Our technique has like 99% of accuracy here. And then this is the result of tamper coincidence. Our technique is better in term of the CBR, tamper coincidence block ratio. And then this is one for PSNR. For recovered image quality, our techniques is perform better than other technique here. So, and this is one for SSIM. This is our publication in this method of research. We have published like 1, 2, 3, 4, 5, yeah, 5 Q1 as me as the first author. Actually, we have AuSR 5. If you can see here, we have version 1, AuSR 1, AuSR 2, and AuSR 3. And this one AuSR 4 currently under review. We have AuSR 5 in the next year, inshallah. And then this is me for the second author. We have published 4 paper in this topic of research. Okay, thank you everyone.